Welcome to AI Frontiers, where we explore the cutting-edge research reshaping artificial intelligence. Today, we're examining 17 groundbreaking papers published on November 29, 2025, focusing on a fascinating paradox: AI systems learning the art of selective amnesia. These papers represent breakthroughs in neural network pruning, selective memory removal, efficiency innovations, robustness improvements, and privacy-preserving techniques that are defining the future of intelligent systems. Picture this. While you were sleeping last night, artificial intelligence systems around the world were quietly learning to forget, not in the way humans forget where they left their keys, but in a deliberate, surgical way. These AI systems now perform what can only be described as digital brain surgery, removing specific memories while preserving everything else they've learned. This isn't accidental forgetting. It's a controlled, precise process that has breakthrough applications in privacy, compliance, and data protection. The technology represents the digital equivalent of selective amnesia, where machines can deliberately erase particular information without damaging their overall intelligence or capabilities. These 17 papers represent the frontier of AI research, emerging from computer science machine learning, known academically as CSLG, which serves as the foundational layer for all AI applications. This field demonstrates a fascinating dual nature. It's deeply theoretical, rooted in statistics, optimization theory, and computational complexity, yet intensely practical with applications touching virtually every aspect of modern life. The same mathematical insights that help us understand neural network behavior also enable breakthrough applications in medicine, climate science, and space exploration. Most importantly, this research is democratizing intelligence itself, creating tools that augment human capabilities and solve problems previously beyond our reach. Think of machine learning research as an enormous digital ecosystem, much like a rainforest where different species occupy unique niches and contribute to the whole. In this ecosystem, mathematical theories explaining why neural networks work coexist with practical algorithms powering your smartphone's camera recognition. Each research area, from statistical foundations to real-world applications, contributes essential elements to the whole. Researchers spend years proving mathematical theorems about when and why certain algorithms succeed, while simultaneously developing systems that diagnose diseases earlier than human doctors, predict weather patterns with unprecedented accuracy, and help scientists discover new materials for clean energy. The first major theme emerging from this research challenges the fundamental assumption that bigger is always better in AI systems. Frank-Wolfe optimization enables the creation of sparse, efficient networks without requiring extensive pre-training, a breakthrough that replaces brute force scaling with mathematical precision. This approach is like sculpting a masterpiece by strategically removing marble, but doing so with mathematical certainty rather than artistic intuition. The research demonstrates that sophisticated optimization techniques can create efficient architectures from the ground up, achieving dramatic computational savings while maintaining or even improving performance. This efficiency revolution suggests new pathways for sustainable AI development. The second theme focuses on robustness through an innovative approach, teaching AI systems to recognize their own confusion. Wu and colleagues developed surprise recognition mechanisms for world models, enabling AI systems to detect when they encounter unexpected situations. Rather than trying to prepare systems for every possible scenario and impossible task, this approach gives machines a sense of their own uncertainty. The result is robust operation despite sensor failures, noise, and unpredictable real-world conditions. This self-awareness allows AI systems to maintain performance even when the world doesn't behave as expected, representing a fundamental shift in how we approach AI reliability. Our third theme explores multi-modal learning through what can be described as symphony conductor approaches, AI systems that integrate multiple information sources simultaneously. The AutoBRANE algorithm represents a breakthrough in multitask algorithmic reasoning, solving the persistent problem of task interference, where learning multiple skills simultaneously degrades performance in each. Like a skilled conductor managing every instrument in an orchestra while understanding how they create harmony together, AutoBRANE achieves 28% accuracy gains while reducing computational requirements by 50%. The system shares knowledge when beneficial while keeping conflicting tasks separate, demonstrating that AI can master multiple domains without sacrificing performance in any single area. 4 revolutionary discoveries are fundamentally reshaping our understanding of AI capabilities, challenging long-held assumptions about how these systems work. Mode conditioning achieves 4-fold efficiency improvements by teaching AI systems to explore multiple reasoning strategies rather than defaulting to single approaches. AutoBRANE solves multitask interference problems that have plagued AI development for years. Surprise recognition maintains robust performance by giving systems self-awareness about their own uncertainty. Adaptive unlearning enables precise memory removal for privacy compliance. Finally, Frank-Wolfe optimization creates sparse networks without requiring pre-training, upending traditional assumptions about efficient AI development. These breakthroughs collectively represent a paradigm shift in AI research. Today's featured research comes from Chen Henry Wu and colleagues, whose work on mode conditioning represents a paradigm shift in AI performance and efficiency. Their paper, titled "Mode Conditioning Unlocks Superior Test Time Scaling," addresses diversity collapse, a frustrating phenomenon where AI systems generate multiple solutions that are essentially variations of the same approach. This breakthrough teaches systems to explore multiple reasoning strategies systematically, achieving 4-fold efficiency gains over standard training methods and 10% improvements on mathematical reasoning datasets. The work represents a fundamental shift from single-strategy thinking to multi-modal reasoning approaches, unlocking hidden potential in existing AI systems. The core problem Wu's team addressed can be understood through a simple analogy. Imagine a brainstorming session where everyone keeps suggesting the same ideas repeatedly. Current AI systems suffer from exactly this diversity collapse when trying to solve problems by generating multiple solutions. Instead of exploring different approaches, they produce variations of identical strategies, severely limiting the benefits of additional computational resources. Mode conditioning solves this by explicitly identifying distinct reasoning approaches and teaching systems to allocate resources across these different modes. The breakthrough includes automatic discovery methods that find hidden solution strategies without human annotation, suggesting our training data contains much more diversity than traditional methods utilize. The technical implementation of mode conditioning involves a sophisticated 3-pillar architecture. The first pillar focuses on automatic mode discovery through gradient clustering techniques that identify distinct reasoning approaches without requiring explicit human labeling. The second pillar develops specialized components for each reasoning mode, either through dedicated models or learned prefixes that guide systems toward different reasoning patterns. The third pillar implements intelligent resource allocation strategies that distribute computational budget across modes based on specific problem requirements. This architecture maintains compatibility with existing AI systems, enabling immediate applicability to current workflows while providing flexibility for adaptation to different domains and problem types. These research advances point toward a future that represents a transition from alchemy to chemistry in AI development, moving from trial and error approaches to systematic, principled methods for designing intelligent systems. The efficiency gains from techniques like mode conditioning democratize access to advanced AI capabilities, making sophisticated reasoning available to researchers and organizations with limited computational resources. Robustness improvements through surprise recognition and similar techniques address critical safety concerns for AI deployment in critical applications. Privacy-preserving techniques enable AI applications in sensitive domains, while building trust between humans and AI systems. Theoretical advances grounded in physics-inspired approaches promise more predictable, controllable, and ultimately more beneficial AI systems. This research reveals that intelligence isn't just about having knowledge or computational power, it's about having multiple strategies for applying that knowledge and knowing when to use each approach. The success of mode conditioning and similar techniques demonstrates that strategic diversification of reasoning processes during inference can be more effective than brute force scaling approaches. These efficiency improvements don't require proportional increases in computational resources, suggesting we can achieve better performance through smarter utilization of existing capabilities rather than simply building bigger models. This foundation enables addressing humanity's greatest challenges, from climate change and disease to scientific discovery and space exploration, while making advanced AI more accessible and sustainable. The creation of this research synthesis involved multiple AI systems working in coordination with human oversight. AI synthesis was performed using Claude Sonnet 4 from Anthropic, providing comprehensive analysis of the 17 research papers. Text-to-speech generation utilizes Deepgram's advanced voice synthesis technology for natural audio delivery. Image generation was powered by OpenAI systems to create visual representations of complex concepts. Throughout the process, human expert review ensured accuracy and clarity of technical content. While every effort has been made to maintain precision, some oversights may exist, and we encourage consulting the original research papers for complete technical details and proper academic attribution. Thank you for joining us on AI Frontiers as we explored these groundbreaking developments in machine learning research. I encourage you to dig deeper into these papers yourself. Each contains insights that could spark new ideas or applications in your work. Share your thoughts about these developments online and join the growing community of researchers, practitioners, and enthusiasts shaping the future of artificial intelligence. Your perspective and insights could be the key to unlocking the next major advance in this rapidly evolving field. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv-preprint-server.org, content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv-preprint-server.org.